Welcome to Rotary Pocket Multi-Axis CAM Strategy lecture by Todd Frazee from Sierra College. In this lesson, we'll explore Rotary Pocket CAM Strategy in Fusion, a powerful tool for machining cylindrical parts with high precision. The Rotary Pocket Multi-Axis Strategy enables you to create pockets on curved surfaces by rotating the workpiece around its axis while maintaining consistent tool engagement. This approach is particularly useful for features such as slots, cavities, and pockets on cylindrical components. We'll cover how to set and optimize the rotary pocket toolpath, ensuring the efficient material removal and accurate geometry on round parts. By the end of this lesson, the objectives are that you'll be able to apply the Fusion Multi-Axis tab to apply Rotary Pocket CAM strategies to machine cylindrical shapes in 4-axis setups, and to model CAM in 5-axis CNC mill applications to industry standards, and apply CAM in 5-axis CNC mill applications to industry standards. There are 3 rotary multi-axis CAM strategies, the first being rotary pocket, the second rotary parallel, and the third rotary contour. They're all found under the multi-axis tab in Fusion. Setup for all the rotary multi-axis CAM strategies are very similar, if not almost the same. They must be aligned with the rotary axis motion of the rotary axis machine. And material removal volume is defined by front and back ends in the geometry tab, and diameters on the radii tab, with the rotary contour and rotary pocket requiring inside and outside diameters to be defined, and for rotary parallel only requiring an outside diameter to be defined. The rotary pocket strategy is a roughing operation that allows clearing of large volumes of material on rotary parts. Material is removed effectively when using the automatic step-down option. And tool offset option allows for the cutter to lead into the material, keeping the center of the tool from engaging that material, and cuts a little more efficiently, gets a better chip, and the very center of ball cutters tend to rub a little bit, so it extends cutter life. Automatic step down is an option you have with the rotary pocket multi-axis CAM strategy. It varies the step down between a maximum step down and a minimum step down value, so that the step downs coincide with the cylindrical floors on the part. It requires you to enter a minimum step down, and as shown on the right, we have the automatic step down. We have an image above of the part without toolpath, and then with the toolpath applied below, and you can see it has 3 passes, and one of them coincides with a floor, so it evenly broke the space up in between them. There's another option that's step down on floors, and it adds an additional step down on cylindrical floors, and make sure that they're cleaned up, but it doesn't go all the way around the part necessarily at that step. In general, on regular cylindrical parts, using automatic step down will result in fewer step downs than using step down on floors. In this case, automatic step down may be preferable, as fewer step downs provides quicker machining time. Now let's apply the rotary pocket multi-axis CAM strategy and a demonstration. Okay, in this video we're going to set up stock for our rotary axis and then set up the rotary settings, which should be similar if not the same for all three of the multi-axis rotary commands. We're going to use a stock file. We're going to go to the data panel. We're going to go to CAM samples. We're going to go to machining extension. And we're going to open this 4th axis rotary file. These are write protected, so you can't save them. You could do a save as if you like, but if you want to save your work. Now this was set up for a tutorial on a live tooling lathe, so it's turning and milling operations. We're going to use this for 4-axis rotary. So we're not going to use anything that's in the setup, and we're going to create our own setup. Notice the orientation is on the left-hand side, so that would be correct if we were on a vertical mill with it on the left-hand side, if the z-axis was in the correct orientation. But on a lathe, the z-axis is in line with the primary spindle, not the tools. So we're looking at this basically backwards and upside down in orientation. So what we're going to do is we're going to create a new setup, and we need to go down some of the options on the first tab. Now this, if you're doing milling, this probably defaults to milling, but this is on turning or mill turn. And we want to switch to milling. Okay, and that's going to change our z-axis to be by default 90 degrees from the existing part. We're then going to go to, we're going to keep the body of the model the way it is, and we're going to come back to this tab. We're going to go to the stock tab, and we're going to deselect from the previous operation because we don't want the information from the lathe axis in here, and we're going to go for a relative size cylinder. Okay, and by default that's going to put that in the z-axis. We actually want to change the axis that that's going to be referencing. So we're going to check the select axis, and we're going to select what we want to be in the axis of the rotary. So if we pick this inside cylinder, that makes the cylinder orientation to our existing part. Now we want to flip this around like it's for a Haas with the rotary on the right. So with this orientation, we're going to go to setup in the front, and we're going to change from model orientation to ZX axis plane. And we don't have anything square that we can pick on unless we have the model of the machine. But if you zoom out and your planes are visible, we're going to use the what is the XY plane to set Z. And then we're actually going to flip the Z, okay, so that it's opposite orientation. If we don't do this, the orientation for what front and back of the stock will not change. And then we're going to select our x-axis, which will be the same cylinder, and that points it in the correct direction if we were to rotate the model around and look at it as if it was on the Haas table with the rotary on the right, X positive pointing towards it. We go to our stock parameters, and if we've done this correctly, on the back side of the material we should be able to put, say, 2 inches, which will go inside the collet holder. And on radial, 40 thousandths is fine. And on the front side offset, we're going to put 40 thousandths as well, so our cylinder automatically go past the model by about 40 thousandths. Now typically the stock's going to be even inch diameter that you start with. So if we wanted to, we could adjust this radial stock to get to exactly 1/2 inch. To add radial 0.125, which will give us a full 5 inches, just so it's an even bar stock size. Okay, Of course, you would set your post-processor information if you're doing that for a real program. We're going to skip over that for the purpose of this demonstration. And we're going to go back to where do we set our box point. So we're going to go to a stock box point, and for this, to make it convenient, we're going to put it on the front center, and that is important for the rotary axis, that it's in line with the actual rotary axis. Now, for these advanced commands, multi-axis, your part does not have to be perfectly cylindrical. It'll use a tool diameter, dynamic worth offset, and dynamic tool length control. So you could literally cut something off center. But if you're close to circular, you're going to get better results accuracy wise if it is lined up with the center line of the rotary axis. If the machine has MRZP, it should be anywhere along here on this axis is where the MRZP point needs to hit touch. Okay, so that's our stock, and we're going to hit OK. All right, and so we've got our stock set up. Now let's go into a rotary command. So for this example, I'm going to use Rotary Pocket, which is one of the default ones, but I believe the settings are pretty much identical. So what we're going to do is we're going to first go to Geometry tab, and it defaults to not knowing where the axis of rotation is. So we don't want our rotary axis set up in line with Z for this particular machine. We want to go in the same axis as our rotary axis. So we're going to select rotary axis, and that's already set up, so it puts the front of our stock clearance plane here in the back inside the chuck, which is where the actual stock is being held onto. Now we can choose to adjust these offsets. Right now they're at 0. So if we want our geometry boundary to go over the edge of this, we can do that. If we want to bracket where we're machining to, like say just to the end of the part here, we can change the stock back, or the back of our cutting routine. We can set it, instead of to stop back, which is based off our stock parameters, we can do selection or model back or model front. So we're going to do model back because we don't want to cut any farther than the model itself on center line with our rotary cutter. And then on front, we're just going to go at flush with the front because we don't need to roll totally over the edge. Okay, but if you needed to, you could push these planes out. Think of this as bracketing the machining of this command between these two circles. Now you can also set a machining boundary of selection. So if you wanted to, say, just machine between these two faces with a command, you could select those. I'm going to elect not to. Okay, so our radius information, this is where your different clearance planes will come from. So we're going to machine from the outermost of our stock OD because we're starting with stock. And then your inner radius, we can go stock ID, inside diameter, model ID, or fixture ID. Now on our material here, the model ID is inside of this shaft. So say we don't want to go all the way to that area, you can change this setting to pick a variety of different things. So in this case, I'm going to hit selection, and I'm going to hit the bottom of this fillet here. So with this rotary command, it's going to cut between this large radius and this smaller radius, but it won't go any deeper than that. Okay, let's go ahead and hit OK. And that completes the setup portion of this rotary command. Okay, this is a demonstration of the cutting parameters for the Rotary Pocket command, and we'll pick up where we did left off on the setup. So we set our geometry, we set our radii. Now we're going to go to the passes command. Now, Rotary Pocket is good for clearing large amounts of material, so we're going to have a 1/4 inch ball selected. And currently, our step over is 1/8 of an inch. So that's the frequency in which it's going to step over horizontally. That is about half the diameter of the cutter. For demonstration purposes, I'm going to go a little bit bigger so we can get a coarser view of this. And we're going to go 200 thousandths, which is close to 80% of the cutter diameter. And we have our different options. We have minimum cutting radius we can put in, minimum final cutting radius. We can do direction both ways or just one way. We can go order by depth. There's different styles. So we have an offset style and we have spiral. So we'll look at both of those. And then there's step downs. Currently we're set at 25,000 step downs. For this, let's try 0.25. We're going to make that bigger. And then cutting move approach. Now it's asking, do you want to go beyond limit, the front line, and back line. So we set the front and back of the part being the front and back of the actual part, not the stock. If you want it to cut with the ball cutter beyond tangency, you would select this box. If you deselect it, then the tangency of the cutter will stop on a plane parallel to that edge. We're leaving stock to leave. This command is intended for roughing. So this is leaving 20 thousandths of material for another operation to come back and clean up. Okay, we're going to go ahead and go to the next tab, the linking tab. We got different policies, full retraction, or you can do minimum retraction. You can keep the tool down. Transition type smooth, so it'll go in an arc shape as it leads in and leads out. Ramp type is currently set as currently automatic. We're just going to leave that. And then we have lead-ins and link modes. Right now it's allowing it to go beyond the front limit but not the back. I'm okay with that because it's going to be over here on the left. Okay, let's hit OK and see what we get. Alright, so we get several moves, and it looks like a phonograph record. It can only get into the areas that the ball cutter can fit. So if I were to hide the toolpath, this is sort of what you result with. Now, you notice there's some pieces floating out there that material would go away. But it is leaving some islands. So this resolution is probably a little too coarse. So let's go back. Let's open this file. And we're going to go to our passes and we're going to see if we get a different result. We're going to stick with style offset, but let's do offset and spiral and see what's different about the toolpath. Okay, so we get a little bit different pattern. Allows it to go in a little bit different orientation. All right, let's go back to the command and let's increase our step over, or decrease our step over. And we'll go back to the default, which is 125. Okay, that's half the diameter of the cutter. Okay, and we have fewer islands and whatnot. Now, if we simulate this, let's take a look at what it looks like. So you notice it's cutting, like it's climb cutting, which is good. Looks like we have some collisions detected. We'd have to look at what the settings are on that. It's perhaps the tool diameter is. It could be that the tool holder as modeled was hitting. Now it's going into doing some of the details, so it's allowing it to move in both directions. For roughing, that's fine. Now it's doing the groove. Okay. So if you have a part that's most likely cylindrical like this, it might be a good option for you to use. And again, this command allows you to set the limits so that this command does allow you to do this command on an eccentric shape. Now I'm looking at this and it looks like I should have worked on my limits and not had it cut over here where you see this cut. So I have to play with the settings so it actually stops right about here and doesn't dive over the edge. But that's a relatively quick fix. And I believe that's where the collision detection detected that it was hitting non-cutting flutes. Alright, so we're going to exit the simulation. And that concludes the demonstration I have for the Rotary Pocket command. Okay, I hope this demonstration of the Rotary Pocket multi-axis cam strategy was helpful for you. In this lesson, we explore the Rotary Pocket cam strategy in Fusion, a powerful tool for machining cylindrical parts with high precision. The Rotary Pocket multi-axis strategy enables you to create pockets on curved surfaces by rotating the workpiece around its axis while maintaining consistent tool engagement. This approach is particularly useful for features such as slots, cavities, and pockets on cylindrical components. We covered how to set up and optimize the Rotary Pocket toolpath, ensuring efficient material removal and accurate geometry on round parts. In conclusion, by the end of this lesson, you were able to apply Fusion multi-axis tab strategy to apply Rotary Pockets cam strategy to machine cylindrical shapes in a 4-axis setup. You are able to model in 5-axis CNC mill applications to industry standards and apply a cam in 5-axis CNC mill applications to industry standards. Hope this lecture was useful for you, and we'll catch you on the next one.